Video is the Chapter 6 multiple choice review video. We're going to be talking about how to look at chance processes and turn those chance processes into random variables, which are variables that have numbers, that have probabilities associated with them, and we're going to take a look at the distributions thereof. So a distribution of probabilities which could be associated with random variables. Let's start taking a look at these questions. First question is choosing an American household at random and letting the random variable X be the number of cars, including SUVs and light trucks. So here's the probability model if we ignore the few super rich people that own more than 5 cars. So the number of cars 0, so the probability of finding a household that has 0 cars is 0.09. The probability of finding a household that has 3 cars exactly is 0.13, and so on. What percent of households have more cars than the garage can hold? Well, it says 2-car garages here, 2-car garage. So what percentage of households have more cars than the garage can hold? Well, it's 3, 4, and 5. So we add these probabilities together. We got 13, 5, and 2% respectively. That's 20% total. Okay, not that bad. For question 2, we're looking at that same probability distribution. What is the expected number of cars in a randomly selected American household? Remember that the expected value of a probability distribution is the same as the mean of that probability distribution. And there's a formula for it. And here's the formula. Remember, we're taking mu sub x, which is the mean of the probability distribution, which is also known as the expected value of that random variable, which is all of the individual values of the random variables times their probabilities, respectively, and then adding them all together. That's the sum of all the individual values times the individual probabilities. So what we can do is do 0 times 0.09 plus 1 times 0.36, etc. And if you were to do all these multiplications and additions, you would get C, which is 1.75. All right, moving forward. That's how to find the mean of a probability distribution, and later on we'll talk about the standard deviation of probability distributions. For question 3, a deck of cards contains 52 cards, of which 4 are aces. You're offered the following bet. Draw 1 card at random from the deck. You win $10. Wow, that's pretty good if the card drawn is an ace. Otherwise, you lose $1, okay? So we need to figure out the probability of winning and losing. Well, as it says here, the probability of you winning, well, winning is card drawn as an ace, so there's 4 aces in the deck out of 52. Seems to me the probability of winning is going to be 4 out of 52. And you either draw an ace or you don't, right? It's either going to be king, queen, jack, 10, etc. So losing is going to be 52 minus 4. That is 48 divided by 52. So those are the probabilities of winning and losing. Let's assign these to random variables. And there's pretty easy random variables here. Winning $10 is positive 10. Losing $1 is negative 1. So here are our random variables. So if you make this wager very many times, what will be the mean amount that you win? Remember, the mean amount that you win is otherwise known as the expected value. So the mean amount that you win, same idea as the expected value. All I'm going to do is probability times payout plus probability times payout until I get all the probabilities and all the payouts, which is, in this case, there's only 2 of them. And performing this calculation, I get negative 0.15. So about negative 0.15, that's the correct answer, which means on average you lose about 15 cents every time you play. So notice that it said if you make the wager very many times, that means that in order for this probability distribution to hold, that answer to hold rather, you're going to need to do it a lot of times, right? And then we were talking about the average of each individual play would be 15 cents lost. Moving on to question number 4, the deck of 52 cards contains 13 hearts. Here's another bet. You draw 1 card at random from the deck. If the card is a heart, you win $2. Otherwise, you lose $1. Let's compare this wager, which is wager 2, with the previous exercise called wager 1. Let's call this wager 1. And recall the expected value of wager 1 is negative 0.15. So it's a bad bet because you expect to lose 15 cents every time you do it. Wager 2 is this one about the hearts. So let's take a look at what this looks like. Just as a reminder, wager 1 has an expected value of negative 15 cents. The probability of winning in this case is 13 out of 52 because there's 13 hearts out of 52. We could also call this 1 out of 4 if you wanted to, right? Because every 1 out of 4 cards is a heart. And then there's 3 out of 4 cards that are non-hearts, we call them. So let's figure out the expected value of this game. In order to do that, we calculate the probability times payout and add them all together. That's negative 0.25. So in other words, if you play the first wager, you expect to lose 15 cents every time you play. If you play the second wager, you expect to lose 25 cents every time you wager. So As you could probably imagine, you don't want to play either of these two games. But if you had to choose, you would probably choose wager 1 because you're losing less money per situation, right? So we're calling question number 4 answer A because it has a higher expected value. I know what you're thinking. Higher? Well, 15 and 25, 25 is higher. Well, not really, because negative 15 is higher than negative 25, right? Higher expected value. All right, moving forward. Question number 5, it talks about the number of calories in a 1 ounce serving of breakfast cereal. I don't know who would eat only 1 ounce of breakfast cereal in a sitting. That seems like a psychotic thing to do, but whatever. The random variable has a mean of 110 and a standard deviation of 10. And we know that the number of calories in a cup of whole milk is has a mean of 140 and a standard deviation of 12. For breakfast, you're going to eat 1 ounce of the cereal with 1/2 cup of whole milk. And T is the random variable that represents the total number of calories in the whole breakfast. Okay? So let's write out an equation that represents T in terms of the cereal and in terms of the milk. So first let's define the variables. T is the total number of calories in the breakfast, M is the total number of calories in the milk, and C is the total number of calories in the cereal. So it seems to make sense to me that C plus M is going to be equal to T because the calories from the breakfast are coming from the cereal and from the milk. Extending that, we can say that the mean of the random variable for calories of cereal and the mean of the random variable for calories of milk is going to equal the mean of the random variable for total number of calories. That looks like this. All right, so since we're combining two random variables together, we can just add their two means together. Oh, this plus should be an equals. Let's change that up here. So like I said, we're adding the two means together. I know that the mean of the cereal is 110. The mean of the milk is 140. So that mean here for the total should be 250. So the correct answer for this one is going to be choice E, which is 250. Bada bing, bada boom. And one thing to remember for this situation is a phrase that we use in statistics, which is the mean of a sum is always equal to the sum of the means. The mean of a sum, in this case the sum is C plus M, is always equal to the sum of the means, the mean of C and the mean of M. That's how that works. Question 6, same situation. Let's say for breakfast you eat 1 ounce of cereal with 1/2 cup of whole milk. So what we're doing here is we are changing, same 1/2 cup of whole milk. The question says the standard deviation of T is, well, in order to get the standard deviation, it's a little bit less straightforward. You can't just add them together. First of all, we can write down the standard deviations of both of the cereal and the milk, respectively. Now we're going to try to combine them together in order to get the standard deviation of T. One thing that we know is combining standard deviations, whether it's adding or subtracting two random variables, we actually have to combine their variances instead of their standard deviations, and this is the rule. So what we could essentially do is change these into variances, add them together, and then square root them to get the standard deviation of the sum of the two random variables. So we can easily square each of these standard deviations to get the variances, 100 and 144 respectively, and then we can combine them to get the variance of the combination of the two random variables. So a fairly straightforward procedure to add these two variances together. 100 and 144 is 244. Now that we have the variance of T, the random variable that is the total number of calories, we square root it to get the standard deviation of T, which gives us 15.62, etc., and so forth. Correct answer is choice C. All right, moving on to question number 7. Joe reads that 1 out of 4 eggs contains salmonella. Yuck. So he never uses more than 3 eggs in cooking. Interesting. If eggs do or don't contain salmonella independently of each other, the number of contaminated eggs when Joe uses 3 chosen at random has the following distribution. Well, you have a situation in which you know that you're choosing 3 eggs every time. 3 chosen at random, right? So this is a set number of trials. You also know that the eggs are either contaminated with the bacteria or not. So it's a binary situation. Let's say eggs do or don't contain salmonella independently of each other. So one egg doesn't inform us of another egg's outcome. So that's independent. And we also know that the probability of success, or I guess in this case of getting salmonella, is 1 out of 4. Sounds to me like this is a binomial distribution. So we know for a fact that this is a binomial distribution. It's not geometric. Why do we know it's not geometric? Because we're not picking eggs until we find one that has salmonella. We are picking 3 eggs every single time. All right, and now we know that the number of trials in this case is going to be 3. So that means I can eliminate choice A, because that says the number of trials is 4. It's either this one or this one. And we also know that the probability of success, I guess if you call it the probability of success when it's talking about salmonella, is 1 out of 4. 1 out of 4 is 0.25. That's, in other words, 1 out of 4. Not 1 out of 3, but 1 out of 4. So here's your correct answer, choice B. Moving on to question number 8. He never uses more than 3 eggs in cooking. Same exact situation. The probability that at least one of Joe's eggs contain salmonella is about, well, at least one of Joe's 3 eggs contain salmonella. So at least one is a success. So we could interpret it in a couple of different ways. One way to calculate it is calculating the probability of 1 plus the probability of 2 plus the probability of 3. But maybe a slightly easier way to calculate it is like this. In other words, it's 1 minus the probability of 0. So I think I'd prefer to do this one because it prevents me from having to do all those multiple calculations. So I can do this on my calculator. And you'll recall in the calculator we use a function called binomial PDF for binomial probability. So we scroll down to where it says binomial probability. And it takes a couple of arguments. Trials is the number of, in this case, the number of eggs he's picking. He's picking 3 eggs. So n is equal to 3. The probability of success, or in other words, finding a salmonella egg, is 1 out of 4. You could also put 0.25. The x value, in this case, I'm trying to find the probability of 0, so I'm going to put 0. And then let's figure it out. 0.421875. So that means, let's put this always in front, good. That means that the probability of at least 1 is equal to 1 minus the probability of 0, which is 0.421875. And that math gives us 0.578125. You can see it on the calculator here. Looks like the correct answer is 0.58. So there's our answer, choice C. Moving on to question number 9. Each entry in the table of random digits, like table D, remember table D? Oh man, from all those years ago, seems like years, has a probability 0.1 of being a 0. And the digits are independent of each other, which means the first digit doesn't affect the next digit. You could have a 0 and then a 1, a 0 and then a 2. You could even have a 0 and then a 0. It doesn't really affect each other. The mean number of zeros in a line 40 digits long. Well, in this case, we're talking about a binomial distribution. How do I know it's binomial? I know it's binomial because it satisfies bins. Binary outcomes, independent, number of trials set, and success probability is also set. So let's take a look at what we know from this problem. We know that the probability of success is 0.1. Here's my P. And I also know that 40 digits long, that's my N, right? That is the number of trials. So I'm able to use a probability formula again, just like what I used in the previous problem to figure this one out. So let's bring the calculator back over here. We are trying to figure out the mean number of zeros in a line 40 digits long. Oh, actually, we're not going to use binomial PDF. We're going to calculate the mean using the formula for binomial random variable mean. Now, the mean of a binomial probability distribution is found on the formula sheet. Here's the formula sheet for the AP Statistics exam. You'll get this. And you'll also need to know how to pilot it, how to find your way around. So let's look under probability distributions. We're looking at binomial distributions. I'm told that the mean of a binomial distribution is equal to n times p. Very straightforward stuff. So I'm going to use that same formula here. I'm using n times p. So in a fairly straightforward procedure here, we should be able to get that the mean of the probability distribution of a binomial random variable is just n times p, which is 4. Boom. All right, moving on up. Question 10. Each entry in the table of random digits has the probability 0.1 of being a 0. Same idea. 10 lines in the table contain 400 digits. The count of zeros in these lines is approximately normal. Wow, a distribution which is approximately normal. So what we're really doing here is taking one line in the table, which we said has 40 digits, and really multiplying that by 10. So for each of these measures, the measure of central tendency, the mean, and the measure of spread, the standard deviation, we're multiplying those numbers by 10. Now we already know the mu sub x, the mean of the probability distribution for the number of zeros in the chart, is going to be equal to 4. If I multiply that by 10, sorry, I should clarify that x is the number of zeros in one line. What I would have to do in order to get the new random variable, I'd have to multiply this number by 10. So mu sub x times 10 is going to be equal to mu sub y, which is mu sub y is equal to 40. So I can go through and cancel out all the ones that I know are not correct. It's not this one, and it's not this one. In order to find the standard deviation, let's look back at that formula sheet to try to find the formula for standard deviation. I know that mu sub x is equal to n times p, but the standard deviation of a binomial random variable distribution is the square root of n times p times 1 minus p. So we'll use that formula now. In this case, we're finding the standard deviation of the random variable x. If you recall, n is equal to 40 because there's 40 digits. P is equal to 0.1 because the probability of getting a 0 is 0.1. And 1 minus p is going to be 1 minus 0.1, which of course is 0.9. So the correct answer looks like this. So I get 1.897, etc., etc., etc. So that's the standard deviation of the original random variable, which is the number of zeros in one line. However, in this case, we're looking for the standard deviation of y, which we're talking about the number of zeros in 10 lines. Well, that means we're going to take this standard deviation and simply multiply it by 10. Because as you'll recall, when you're multiplying a random variable by a number, you also multiply the mean and the standard deviation by that same number. Addition works differently, but multiplication works just like this. So here's our correct answer, which to me looks a lot like 19. So my standard deviation is 19. Choice B is our correct answer for number 10. Moving on to number 11. A psychologist studied the number of puzzles that subjects were able to solve in 5 minutes while listening to soothing music. Let X be the number of puzzles completed successfully. So it could be 1, 2, 3, or 4 here. Surprising that nobody was able to solve more than 4 puzzles in 5 minutes. I guess we don't really know what the puzzles are. The X has the following probability distribution, which is here. What's the probability that a randomly chosen subject completes at least 3 puzzles? At least 3. So this one and this one in the 5-minute period while listening to soothing music. Well, 0.3 plus 0.1, that's 0.4. Pretty straightforward, if you ask me. All right, question number 12, same situation. Suppose that the 3 randomly selected subjects solve puzzles for 5 minutes each. The expected value of the total number of puzzles solved by the 3 subjects is. Well, remember that expected value is the mean of the probability distribution. At least that's what this says. So in order to find the mean of the probability distribution, I'm going to multiply all of the values of x, the random variable, times all the probabilities. Here's how it looks. So I'm multiplying all of the values of x times all the probabilities. At the end of the day, I get 2.3 as my answer, which means the correct answer is choice B. Excellent. All right, suppose a student is randomly selected from your school, not Queens Metro. Which of the following pairs of random variables are most likely independent? We're looking for variables that do not affect each other in any way. Let's take a look at them and see which ones are going to be independent. First, x is going to be the student's height. Y is going to be the student's weight. Well, it seems to make sense that if a person is taller, there's probably more of them. So in general, their weight should be higher, right? If I have a friend that's 6'10", for example, their weight is probably higher than mine because I'm less than 6'10". So this one is most likely not independent, right? Your height and your weight are both physical characteristics that are affecting each other. X is student's IQ, and Y is student's GPA. We know that IQ is sort of a not great measure of somebody's quote-unquote intelligence, even though it is called the intelligence quotient, and their GPA. In general, you would assume that if a person's IQ is higher, that means they scored high on an IQ test. That means their GPA is probably higher because, you know, your grades are basically based on tests. So these are both measures of a student's quote-unquote intellectual capacity, whether that's a real thing or whether it's not a real thing. So you would assume that these two are affecting each other. For letter C, students PSAT math and PSAT verbal. If a person takes a PSAT prep course or is overly good at tests, then their PSAT math score would probably inform us that their PSAT verbal score would probably be similar. I know that they're different topics. However, knowing how to take a test affects both of these things. So since one aspect affects both of these scores, I would not say that they are independent of each other. X is the average amount of homework the student does per night, and Y is the student's GPA. You know that if you do more homework, you will do better in the class. Not just because you learn more, but because you will have a higher grade in homework, right? Average amount of homework the student does per night, well, if they do more homework, that means their GPA probably is affected by that. Or in other words, both of these are, they would vary, they would have a positive relationship between them, right? They vary directly. So that's probably not it either. Leaving us with letter E, and this one is the one that makes the most sense, why it would be independent. Average amount of homework the student does per night, and student's height. Listen to me. I've had great students that are super duper tall. I've had great students that are super duper short. Their height is definitely not something that is related to in any way the average amount of homework, right? So since these things are not related, since one outcome is not going to affect another outcome, I would say this one is the most likely independent event, or most likely independent random variable. Moving on to question 14. Certain vending machine offers 20-ounce bottles of soda for $1.50. The number of bottles is X, and we know that the random variable is mean of 50 and the standard deviation of 15. Let's jot that down right away. And we know that the random variable Y is the total revenue from this machine on a given day. Seems like the revenue would be the number of bottles sold, which is X, times $1.50. Assuming that the machine works properly, what's the mean and standard deviation of Y? Well, we know that each of these values, the mean and the standard deviation, are equally affected by a multiplication from the random variable. $1.50 times X is going to mean $1.50 times mu sub X, and $1.50 times mu sub sigma sub X as well. So that calculation is fairly straightforward. 50 times 1.5 is 75, and 15 times 1.5 is going to be, what is that, 22.5? You add another 7.5 to it. So the correct answer is here. That would be choice D. Right? We just multiply each of them together. The weight of tomatoes chosen at random is the random variable with mean. Mean is mu is equal to 10, and standard deviation S is equal to 1. Let's see. Suppose we pick 4 tomatoes at random from the bin and find their total weight. So what we're doing is adding the weights together. So this is how I'm going to symbolize it. The mean of the first plus the mean of the second plus the mean of the third plus the mean of the fourth is equal to the mean of the total number of tomatoes. So what we need to do is take all of these means. We know the weight of an individual tomato is a random variable with mean of mu is equal to 10. So all we need to do is substitute all of these for 10 and then find that mean of the total. And I know that this might seem a little childish, a little straightforward, but the reason that they're testing you on this is that they're trying to figure out whether you know that the sum of the means is equal to the mean of the sums. That's what we talked about before. All right, moving on to question number 16, which also talks about the weights of tomatoes. We're trying to figure out the standard deviation. And if you recall from before, standard deviation doesn't work the same way as mean. We know that combining standard deviations isn't the way that we can do it, but we can combine the variances of random variables. In this case, we're combining the variance of the random variable for tomato number 1, for tomato 2, tomato 3, and tomato 4, and then we get the variance of the total weight. And then once we get that variance, we can square root it to find the standard deviation. So let's do some substitutions. Now, admittedly, this was not that difficult to figure out because 1 squared is just 1, etc. and so forth. So I got the variance is going to be equal to 4. That means that if I want to find the standard deviation, which is the variance square rooted, all I have to do is square root 4, which gives me 2. Not that bad. Fairly straightforward. That was question 16. This is really just quizzing you to figure out whether you know how to combine the standard deviations of random variables. For question 17, which of the following random variables is geometric? And you remember the hallmarks of geometric are as follows. It's almost exactly the same as a binomial distribution. Still binary outcomes, still independent events, still a set probability of success, but the number of trials are not set in advance. It's a shoot till you miss kind of thing, or you keep doing it until you get the success that you're looking for. The number of times I have to roll a die to get 2 6s, the number of digits I read in a randomly selected table until I find a 7, and so on and so forth. Let's pick these apart. Well, remember, we know that the number of trials are not set in advance, so this says the number of 7s in a row of 40 random digits. That sounds like n is equal to 40, so we're not doing that one. The number of 6s I get if I roll a die 10 times, seems like 10 times is the value of n, the number of trials, so that's not it either. And remember, they must be independent events. The probability of one, or the outcome of one, doesn't affect the outcome of another. If I deal cards from a well-shuffled deck of 52 cards, I'm going to start from 52 cards, then I'm going to have 51, then I'm going to have 50. So that seems like the outcomes are not independent. They are dependent on each other. So now we come down to either A or C, and C is the correct answer because we're looking for one specific value, either a 7 or not a 7. This says to get 2 6s. We're not trying to get multiple successes for geometric distributions. We're trying to get one success. You keep going until you hit to get one success. The correct answer is choice C. And last but not least, 17 people have been exposed to a particular disease. Yuck. Each one independently has a 40% chance of contracting the disease. That seems like a probability to me, so I'm going to say P is equal to 0.4. And reading backwards a little bit, this says 17 people. That seems to me to be the number of trials. So this tells us that the hospital has the capacity of handling 10 cases of the disease. What's the probability that the capacity will be exceeded? Well, the probability that the hospital's capacity will be exceeded is if the number of successes, people that are sick, is greater than 10. So 11 or 12 or 13 and so on. So hospital's capacity being exceeded, that probability is the probability of 11 sick people, 12 sick people, 13 sick people, and so on. Now, there was an easy way to do this before. We just did 1 minus a probability, but in this case, it would be 1 minus the probability of 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So this looks a little cumbersome. Luckily for you, there's a calculator shortcut for this. Previously, we've talked about using the calculator to do binomial PDF, which of course lives in the distribution menu. And binomial PDF finds the probability of one specific outcome. So if I were to try to do this using binomial PDF, I would have to do 1, 2, 3, 4, 5, 6, 7 calculations, right? I would have to put in the number of trials, which is 17. I would have to put in the probability of success, which is 0.4. And I would have to put in an X value of 11, and then find that, and then add to that the probability of 12 successes, the probability of 13 successes. That's a little cumbersome. There's another formula in the calculator, though, that works similarly to binomial PDF, and that's binomial CDF. Binomial CDF is a cumulative probability function, easy for you to say, and it works by finding the probability of a certain X value, a certain value of the random variable, and all of the variables values below that. So I'm going to put in 17. I'm going to put in P, which is 0.4. And what I want is an X value that below which I'm looking for all of the probabilities. So let me make it a little bit more clear. So binomial CDF finds the probability of a certain value of a random variable and all values below it. This looks like I'm going upwards. However, I can rewrite this so that I can use it for binomial CDF. Another interpretation of binomial CDF is this. The formula binom CDF n, p, and x gives you the probability that the random variable is less than or equal to that value of x that you used. So, I don't have a less than or equal to here, but I can rewrite it as a less than or equal to by using the trick I used before, the complements rule. The probability that the capacity is exceeded is the probability of 11, 12, 13, 14, 15, 16, or 17 for the random variable. In other words, 1 minus the probability of x is less than or equal to 10. 1 minus the probability that the capacity is not exceeded, right? If it's 10 or under, the hospital is okay. So now I can take this probability of x is less than or equal to 10 and find this out using my calculator's binom CDF feature. So binomial CDF asks me for the number of trials, which is 17. That's easy. The probability of success is 0.4, which I guess I should change from 0.04, huh? 0.4. And the x value is 10. In other words, I'm looking for the probability of 10 and all the values below it. Pasting that in, I got 0.96518, etc., and so forth. So I can replace the probability of x is less than or equal to 10 with what I just found in my calculator. Now let's just do the subtraction. Well, I know that it's not letter D, and I know that it's not letter E. But let's do the subtraction anyway. It seems to me that 1 minus the probability that x is less than or equal to 10 is 0.0348. Looks like 0.035 to me. Alrighty. Well, that does it for this video. We are done with the multiple choice review. This was the video on Chapter 6's multiple choice review. Good luck studying.